Hey, Chem 30. Today we're talking about equilibrium law expressions and what we call the Kc value or the equilibrium constant. So now we're getting into the math of things, which is what we're going to be spending a lot of our time doing, is dealing with equilibrium mathematical expressions and crunching some numbers to try to analyze equilibrium. So our objective for today is to define Kc to predict the extent of the reaction and write equilibrium law expressions for given chemical equations using lowest whole number coefficients. All right, so let's get into it. So first of all, can we use stoichiometry for equilibrium reactions? And the answer is no, we can't use traditional stoich as we know it. And the reason why is traditional stoich relies on the fact that the reaction is quantitative, right? And then if we had a percent yield, we could maybe use that, but percent yield isn't as useful as what you're about to learn, which is how to write equilibrium expressions and equilibrium constants in order to analyze an equilibrium system. All right, so let's get into how this works. To write an equilibrium expression, well, I'm just kind of messing up here. I'm getting ahead of myself. For equilibrium reactions, we must use equilibrium constants and expressions. The equilibrium constant is Kc. K is normally kind of our generic letter for any constant, right? When you talk about, like, for example, Hooke's law in physics, you have the spring constant is K. It's just what we use for constants a lot of the time. And then C, I believe, stands for the fact that we're actually dealing with concentrations here in this law. Now, when we deal with an equilibrium constant, we don't have any units. It's a unitless value, and it's only valid at one temperature. As soon as we change the temperature of the system, we actually have to change the Kc value. So the equilibrium constant is only valid if temperature is remaining the same. And we can look at the Kc value and actually tell from that Kc value if it's a product or reactant favored equilibrium. If it's a product favored equilibrium, then that equilibrium constant is going to be greater than 1. If it's reactant favored, it will be less than 1. But it's always going to be greater than 0, so it's only ever going to be positive. So again, no units, only valid at one temperature, and then it tells us if it's product or reactant favored, product greater than 1, reactant less than 1. So how do we write out our Kc expressions? Well, what we do is first we take a look at the balanced chemical reaction. So for example, if I had a generic reaction that was coefficient of A and then reactant A plus coefficient B, reactant B makes coefficient C, product C, and coefficient D, product D. And then my equilibrium expression is the concentration of product 1, product C, in moles per liter, but I don't write the unit down, to the power of its coefficient when balanced with the lowest whole number coefficients, multiplied by chemical D, concentration of moles per liter, to the power of the coefficient divided by A to the power of A and B to the power of B. So essentially, I just take the concentration of products and I put it to the power of the coefficient. I multiply all those together and then I divide it by reactant mole per liter concentration to the power of its lowest whole number coefficient, right? Multiplied by other reactants doing the same. And when I divide products by reactants, then I get my coefficient, my Kc constant, my equilibrium constant. And then I can know if it's product or reactant favored based on that. But the real power of this is if I know the equilibrium constant for a given temperature, then I can find how much product or how much reactant I have, as long as I have information for all the other different chemicals in the reaction. Okay, so that's the basic layout, and we're going to go through a ton of examples. This is going to make sense if it doesn't already, but a few notes. First of all, you got to have products over reactants. It's not products plus, and I actually hate that I have this little note here as a plus, because it is multiplying, right? It's this to the power multiplied by this to the power. It's not adding or anything, and that's often an option on tests, is it being added together instead. We have no adding here. It's all to the powers, and then we have multiplying and then dividing. We do this with the lowest whole number balancing, so I have to balance the reaction first if it's not already balanced. It's always a lowest whole number coefficient. I can't use fractions for this. It must be in moles per liter, and all concentrations I'm looking at are equilibrium concentrations. So this is for when the equilibrium has been established, okay? Not for like when it first starts out. This is for when I have dynamic equilibrium. So, you know, all the conditions we talked about last day, all the macro properties of color, pressure, temperature are staying the same, right? My concentrations are staying constant, and that's because my forward and reverse reaction rate is equal. So why don't we have units for Kc? The units would be crazy, right? I got all these mole per liters and coefficients, so it's going to change with every single equilibrium that I deal with. So we just get rid of the units. We don't have it, okay? Because of the fact it's not going to be constant units. It's going to work out to these nonsensical liters cubed over meters cubed and weird stuff like that. So we just leave units out of it entirely. Never include in equilibrium expressions solids. We never put in solids, and we never put in liquids if there's only one liquid in the reaction. All right, so I need more than one thing that has a liquid state before I'm going to include liquids. The reason for this is that concentrations in moles per liter don't make sense unless I have things that, you know, I have solutions, right? So if I have solids, I don't have a solution because I don't have particles that are evenly distributed throughout the vessel, okay? So I can't talk about a concentration because I don't have that even distribution. Same thing when I'm dealing with pure liquids. So only if I have more than one liquid present can I include liquids. So when I'm looking at that, I'm looking at all reactants and products. I'm looking at the states. And if there's more than one liquid between both reactants and products, then I include them in the expression. Otherwise, I do not. Gases, aqueous things, they always get included. They're always in the expression. So let's take a look at this. Here I have 2H2O liquid plus sodium produces 2 NaOH aqueous and H2 gas. So we're going to write out our equilibrium expression for this, our Kc expression. So let's take a look first at units and figure out what I have and what I should include. H2O liquid, it is the only liquid. Look at this, liquid, solid, aqueous, gas. So I don't include this in my Kc expression. In the same way, I do not include sodium either. So I've got no products. So what I do is on the products, I put a 1. Yeah, I don't have anything, so I need a 1 there. And then in reactants, I have NaOH aqueous. I'm going to include that because it is aqueous. That is to the power of 2. And then I have H2 gas as well. And that is to the power of 1. I don't have to put that because, I mean, it's a 1, which obviously will be there. So I'll leave it at that. So that's my equilibrium expression. 1 over NaOH squared and H2 gas concentration. This one is imbalanced. We're going to give it a go. I've got H2O2 liquid plus C3H5O liquid gives me 6C6H12O4 solid. I'm going to need 2 of these to make that happen to get 2 carbons. Now I have 10 H's plus 2 is 12 H's, and I have 2 plus 2 is 4 and 4 O's. I'm balanced. So now I have a solid here, which means no, I'm not going to include it. And then I've got 2 reactants that are liquids. So because I have 2 liquids, I can include it because concentrations make sense. So again, I have a weird product here that I don't include. So it's going to be 1 over H2O2 liquid to the power of 1. Don't have to write that. And as a reactant, C3H5O liquid to the power of 2. Just a reminder, when I have these square brackets, that means concentration in moles per liter. We're going to start dealing with numbers really, really soon. So again, if I calculate with numbers a Kc value greater than 1, then that means that the equilibrium favors products. So I'm going to have a higher than 50% yield if I looked at percent yield. If Kc is less than 1, then it's a reactant-favored equilibrium. Now, if I had a reverse reaction, what would the Kc value be for the reverse reaction? Kind of an interesting thing to think about. Well, normally for Kc, I've got my products on top and my reactants on the bottom. So if I'm reversing this, what I do is I had my previous products on the bottom and my previous reactants on top, because this is flipped. My reactants and products have now flipped. So essentially that would be the new Kc for the reverse reaction. So what this means is that if I want the Kc for the reverse reaction, Kc for reverse is equal to 1 over the Kc of the forward reaction. So it's just the inverse. If I inverse the equilibrium constant for that equilibrium, I'll have the Kc of the reverse reaction, which is kind of neat. So let's take a look at an example just so you can see this in action. So if the Kc value for the formation of H2S gas is 40, what would the equilibrium expression in Kc value be for the decomposition of H2S? So all I would have to do is say, well, if I'm looking at formation, that's the opposite of decomposition. So Kc for decomp would be equal to 1 over Kc for formation, right? So I've just got 1 over 40, and of course that is equal to 0.025 as a value. Okay, so that would be my reverse reaction Kc value. So just showing you that in action for reverse reaction. All right, we're going to take a look at actual values here and try something out. So this is in your workbook. You don't even have to write it down. There's a spot for you to go ahead and work out this example. I'm going to get the calculator ready and I will be right back. So let's write out our Kc expression for this and then try to figure out a value. So at equilibrium, H2 gas and I2 gas both have a concentration of 0.22 moles per liter, and HI gas has a concentration of 1.56 moles per liter. Write the equilibrium expression and find the equilibrium constant of the following balanced reaction at 448 degrees Celsius. By the way, that temperature doesn't actually get factored into our work at all. All that means is that if I had a different temperature, I know the temperature is different, and therefore the Kc value will have changed. So Kc is equal to my product, HI gas, and the coefficient for that is 2, so I have that to the power of 2, it's squared, over H2 gas, and that's multiplied by I2 gas. So now I can plug in my values. I have a concentration of HI of 1.56 moles per liter. Now, I do not write the unit. I never show units in my equilibrium expression work. I'm just going to leave it out. So if you were one of those people that forgot units all the time, this is the chapter for you because you don't have to write the units within equilibrium expressions. So I have 1.56 and I have 0.22 and 0.22. Shortcut, could I have squared that, right? And just written it once? Sure, I could have. Now, I know some of you are going to ask, is it okay if I put units in my work? And the answer is no. You're supposed to leave it out. It's technically correct to just leave it out of your work entirely. So 1.56 squared divided by 0.22 multiplied by 0.22. Again, I could have put squared there and that would have been fine. And I get an answer of 50.28. So with the sig digs I have, which is 2, my answer for this is I have a Kc value of 50. Great. That's that question. The next question is, could I use this same Kc value for this reaction at 25 degrees Celsius? That is a resounding no. No, I could not. This Kc value is only good at one temperature for this reaction. So it's specific to both reaction and temperature, and that's at 448 degrees Celsius, right here. Now, a reason for this, for example, well, if I got to 25 degrees Celsius, this I2 wouldn't even be a gas anymore. It would be a solid. So that even changes my expression, not just the value, but the expression completely changes as a result. And you might be thinking as well, if you're really a deep thinker, does this factor into activation energies for forward and reverse reactions? Yeah, it totally does. This has to do with that. So as I have that activation energy hump, right, the forward reaction might still be able to occur, but then the reverse cannot as I lower temperature. So as a result, I might end up having the Kc value go up, right? So it's more product favored, something like that. So it all relates to the energy part of this as well. But we don't analyze that, we don't get into it. All you need to know is that the Kc value is for a set temperature only, and if I change the temperature, the Kc value is no longer valid. All right, here's another value or another question. This is also in your workbook. Take a moment, give this a go, and see how you do. It's weird because it's got teeny tiny values. And here's the solution. Now, this is all ones, but it is balanced, which is really convenient for us. So I have Kc is equal to this iron thiocyanate weird ion thing. So FeSCN 2 positive, and don't let those weird ions confuse you. It's just still in equilibrium. That was a horrible line, but I can't redraw it without a bunch of hassle, so we're just gonna roll with it. Fe3 positive aqueous, that's to the power of 1, and I have SCN minus aqueous, also to the power of 1. So what I have is I have 9.22 times 10 to the negative 4, again, no unit, I'm leaving that out. That's a better line. Divided by 3.91 times 10 to the negative 2, again without a unit, and 8.02 times 10 to the negative 5. When I'm entering this into my calculator, I'm going to be fairly careful when it comes to entering the exponents. So I've got 9.22. I'm going to use the second comma E thing for this, and then put in negative 4. Did I do that right? Yes, I did. And then divided by, I'm going to put brackets here. I've got 3.91 second E negative 2 multiplied by 8.02 second E negative 5. And I get a final answer here. I'm just going to double check my values to make sure that I'm completely on track here. Always good to do before you press enter. Looks good. When I press enter on this, I get an answer of 294. So 294 in correct significant digits. Just to show you how important those brackets are, if I were to second enter to get everything back, and then just sneak those brackets out of there to see what happens, it would not come up with the right answer. And the reason why is it divides by this and then it multiplies by 8.02 times 10 to the negative 5. That's not what I want to do. So really important that you remember your BEDMAS rules, and then you make sure it's dividing by both of these values when you enter it into your calculator so you don't run into problems with your value. So 294 being the right answer. This is kind of a neat question because it's analyzing a graph to get the answer instead of the classic, here's the numbers and you figure it out. So I think this is worth kind of trying out. I'm gonna have to move things around a bit to get some room for doing the work on this slide. But a technician is producing hydrogen gas. He adds methane gas, steam, and a nickel catalyst to an empty reaction container and allows the system to reach equilibrium. The reaction is represented by the following equation. CH4 gas plus H2O gas makes 3H2O and CO gas. And then I have the data. So first thing to realize when I take a look at this, I'm just moving that because now the beginning blurb doesn't matter, is that equilibrium is established right here at 3 minutes because this is when concentrations start to remain equal. During that time, am I still making H2 gas and CO gas? Yes, I am, but I'm making CH4 gas and H2O gas at the same rate. In other words, the forward and reverse reaction rates are equal, which is what I have at equilibrium. So my Kc expression, Kc is equal to H2 gas to the power of 3 multiplied by CO gas to the power of 1 divided by CH4 gas to the power of 1 and H2O gas. These are all gases, so it's all included in my equilibrium expression. But now what I need to do is make sure that I get the values right for plugging in. So based on my scale, hydrogen is 1.800. My CO gas is between 0.4 and 0.8. So this is 0.600. My CH4 is right on 0.400. And then my H2O gas is 0.200. So in this reaction, I started with CH4 and H2O in a vessel that was added in, right, into the vessel, and then it started reacting to make my CO and my H2. You'll notice that the H2 goes from 0 all the way to 1.8. The reason for that is there's 3 for a coefficient, so I end up making 3 times as much H2 as I do CO, right, based on what I got here. So let's plug it in. Let's figure out what the equilibrium constant is. So Kc is equal to my H2 number to the power of 3. So 1.800, I'm going to cube that, multiplied by CO gas, 0.600, that's to the power of 1, divided by CH4, 0.400, also to the power of 1, and H2O, 0.200 to the power of 1. So in my calculator, I am putting in 1.800. Not that I need to put in those zeros, but oh well, we'll do it just to keep it super honest and clear what's being entered. Divided by 0.400 and 0.200, and my brackets for the denominator. I end up with an answer, a Kc of 43.74. I got 3 sig digs here, so 43.7 is my equilibrium constant. This is product favored. It's over 1, so I got a product favored reaction here. And yeah, so I can also do this from a graph, which is kind of neat as well. I just got to read the graph. All right, so that is Kc, constants and expressions. Hopefully that gives you kind of an idea of how that works. Have a good rest of your day.